Okay, hi guys. So we went through the basic idea of rotating a function to end up with circles. And if we add up the circles, we end up with this volume shape. And that's our basic way of coming up with volume. Of course, there's more, geometric ways from geometry how to do it. But this is us taking just a function and creating a shape out of it. It's almost like how do they get a flat image into a 3D image? You give it a little bit of depth to it. And the way we start off learning about this is just in a very basic way, okay? There's a lot of ways of finding volume, but this is our basic way, is spinning things around. So let's go ahead and talk about a simple object of y is equal to x squared. And then I'm going to tell you guys to rotate around y is equal to 0. Okay, from between x is between, let's say 1 and 2. Something pretty easy like this. So we're looking like a shape. And this part's just review, folks. We have a parabola going up between 1 and 2, 1 and 2. And we are going to rotate around the x-axis. So thank you very much. They told us an easy axis right here. That's our x-axis. So when we spin it around, we should get a mirror image. Hopefully you guys can get the visual here, a mirror image. And this mirror image will give us circles like that. Make it a little nicer. Okay, we get a little circle. We're gonna get a little circle inside. So hopefully you guys can see our little volume forming. It's like a little cone. And the point is that we are just adding these slices, adding these circles together. Adding one circle to another. How thick are these circles? These circles are the thickness of dx. Integral from 1 to 2. Right, we're only doing from 1 to 2. And we said, what's the radius? Well, we're adding circles of pi r squared. So it's pi r, which is x squared minus 0, which is just x squared. We don't even need to write the x squared minus 0, do we? Just write the x squared. Don't forget the squared. Oftentimes kids forget the squared because it's squared already. And then we're going to multiply this by a little bit of dx. So just to remind you, this is a base times our height, which is our volume. And the integral adds up all these slices together. Easy peasy. We can simplify it as pi 1 to 2 x squared becomes x to the 4th. And then we can integrate this by hand. Not a hard problem. So if I extend the axis, we said, what if I make the same problem, except I want to change the axis to, well, y is equal to x squared, and we're going to rotate around y is equal to negative 2 versus positive 2. Oh, let's do positive 4, okay? Because 2 squared is 4. Okay? So we're going to do two problems now. We're going to cut these two problems in half, and we'll see, hey, what really changes between the two? And is there really a setup difference? So we'll say axis of rotation is y is equal to negative 2, and y is equal to 4 here. And what happens to the graph? Well, this graph here, we still have our parabola, negative 1, negative 2. This is my new axis of rotation. So 1 and 2. We're going to reflect it. Oops, darn it. Better curve. Okay, and this becomes a even larger disk. Right, because I'm stretching out the radius. On our right here, though, positive 1, 2, 3, 4. Our parabola is going to meet up about right there. Okay, 1, 2. And this is 4. 2 squared is 4, right? We're rotating it going up. So in this case, we're spinning this way. In this case, we're spinning this way. That looks low. Let me do that. Redraw that one. Right, we're rotating up this way. Now, here is my drawing. Let me go ahead and finish up the drawing. Draw a little mirror image here. Ish, right? And then we end up with these circles. Draw a little circle right here. Right? Those are a little disc. Okay, for us to visually look at this, we also want to know what the radius is for both these problems. So the nice thing is that if you have a picture of it, great, easy peasy, right? And it tells us, hey, how do I find the radius? It's really just the function all the way to the axis of rotation here. In this case, we're upper minus lower. So we have the function x squared minus -2. That's my r value. That's the radius, which leads us to a nice x squared plus 2. And it kind of makes sense. This is my x squared here. And if I add plus 2, that's the radius, wherever we're at. X squared plus 2, that's the radius. But up on the right, we want to be careful here, because if we do upper minus lower, you might say, hey, use this function. We don't know what that function is. Do you guys want to go and spin this and find that new function? Nope, I ain't doing that. But we are only looking for this radius here. We're only looking for this value, and the way we find this value is upper minus lower, meaning it's going to be 4 minus x squared. Now, why did I say 4 minus x squared? Well, look, if this whole value from here to here is 4, don't you agree that's just the number 4? And if we just subtract our y value, isn't this y value derived by y is equal to x squared? So it's just 4 minus wherever you are on the graph. What happens at this point where they meet? Well, that'll be 4 minus 2 squared is 4 minus 4. And guess what? The radius is 0. Perfect. I was expecting that there wouldn't be a radius there. So this comes back from geometry. This should make sense. So let's go ahead and set up our integrals. We're going to go the same thing from before. We're going to go from 1 to 2. Integral of pi r squared dx. Integral of pi r squared dx. This does not change. Why? Because we are just adding what shape? We're adding circles. And I want to make sure this seems pretty simple to you. The shape is a circle. We're adding circles. X squared plus 2. 4 minus x squared. Different shapes, different volumes. So every problem has its own setup. So make sure you give every problem its due. Give it some time, making sure you are catching it. Now, all these problems, since they are simple polynomials, we could integrate by hand. Sorry, this needs to go outside. Now, on the AP test, you can always just put the pi on the outside. Remember, that is just a constant. The reason why I always set it this way, because I want to make sure you guys understand, this is not some fancy equation. This is just adding a freaking pi r squared equation problem. And that's where kids get confused. They don't realize that when they see this, they don't realize it's just pi r squared. Okay, easy peasy. Hopefully you guys, I saw a lot of people finish the homework 20 questions in like 60 minutes. Great job. Okay, so you guys will have some axis of rotations that are shifted today. Not super hard, but you have to, here's the problem. If the function's on top, we've been doing this. But if the axis of rotation is on top, you got to spin it around, upper minus lower. And if you don't, you end up with a negative radius, which isn't a big deal when you plug this into your calculator, because when you square it, it still becomes positive. But when you write it out, it doesn't really make sense. Okay. All right, so let's jump to washers now. So we're going to jump to washers. And so let's come up with our problem. Y is equal to x squared plus, let's do 2, okay? And then we're going to be bounding this graph, bounded by y is equal to 2, right? And then we're going to rotate around y is equal to 0. Okay, so let's set up what this graph will look like. I have a graph starting off at x squared plus 2, and if you please notice, that's just a parabola 2 spaces up. 1, 2. That's a parabola 2 spaces up. And this guy's going to flare out like any other parabola. Right? we're going to bound this graph by a second graph, y is equal to 0. No, y is equal to 2, sorry. That's 2. So the idea is this is my graph right here. That is my graph. Okay. Now, if I rotate this graph, we're going to end up with a mirror image across the x-axis here, y is equal to 0. So 1, 2 spaces going down. Let me make this look a little prettier. Just go as a ruler. Oh, where to go? Okay, dot, 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 hi there. And we're going to the other way. And here's what our big circle looks like. Darn it. Okay. But you've probably noticed that we don't have anything here, right? Isn't that a big donut hole? So we have to draw another hole inside. So hopefully you notice that we have a donut hole here. Let me go ahead and draw another one here. With a donut hole inside. Oh, yikes. Oh, it's too small, so I think I'm drawing a... Whatever. Okay. So how do we come up with this shape? And I want to pretty much just tell you the answer. The answer is this is just the two shapes cut out. It's a large shape here. Oh, dang it. It's my fault. I ran out of elbow room. Hey, that's my large shape. Oh, darn it. Hey, and we're going to minus the toilet paper roll here. Okay, we're going to minus the big shape from the small shape. Okay, so how do we set this up? Instead of coming up with a nice fancy equation, I'm going to actually show you guys this done in two integrals. It's an integral that's used from 0 to 2, in this case 0 to 2, of pi r squared dx minus the integral from 0 to 2 of pi r squared dx, where our radius for the first equation will be the integral 0 to 2 pi, we said x squared plus 2 squared. That's how we find the volume of my first shape. The way we find the volume of the small cylinder inside, 0 to 2 pi r squared, we said that was going to be a 2. Okay, now the next step here, I'm showing you guys how they came up with the base formula. This is going to become, since they have the same interval for our integration, we're going to write this as one big integral, 0 to 2, pi x squared plus 2 squared minus pi 2 squared dx for everybody. Hey, guess what? What do they have in common? Don't they both have a pi? Pi integral from 0 to 2 of x squared plus 2 squared minus 2 squared. dx.
So, Mr. Ko, on the last lesson or chapter, we guys use the calculator a lot. On this, if we wanted to just plug the original equation into the calculator, is that okay, or you want us to do it all by hand?
Um, the problems that you receive should be able to be done by hand. But for the learning goal isn't can you take the integral. The learning goal is can you set it up. So you can do it on a calculator or by hand, whichever one you want. Because that's not the goal. The goal is to just be able to set it up. And that's what the homework's going to be. It's going to be, hey, set it up. Okay, so looking here, this is what I want you guys to get to in the end. The formula is simply pi integral a to b of r squared, whoops, minus little r squared dx. That is our formula. Okay. So if we have washers, this is the washer's formula. How they come up with this formula is they just said, we're just subtracting the two volumes. And if you want it, you go from here to here instead. And that's a setup for any washers problem. The only big deal is they have to figure out what your big R and what your small r. And if you don't know what the graph looks like, it's hard to tell which one is which, especially if I change the axis of rotation. Now, if I look at this problem now, let's take a look. I'm going to restart the problem. If I wrote you y is equal to x squared plus 2 and y is equal to 2, these are our boundaries. Okay. Would you automatically know which is the outside and which is the inside? Well, not yet, because I'm going to give you the axis of rotation. I'm going to give you guys two different problems. Axis, y is equal to 0. Okay. And then here, axis, y is equal to, let's do 4 like we did before. No, not 4. It's going to be 6 this time. It's going to be 6, okay? Because 4 plus 2 is 6. So we have two different problems now. What we did before, simply let's draw a graph like what we saw before. This is x squared plus 2. This is 2. We are rotating around the x-axis going this way. You guys okay with that? So we're spinning. And you end up with our shape like that. Okay. Outer, inner. That's our big R. This is our little r. So the setup for this problem is pretty quick. Let's say our interval again is x is between 0 and 2 this time. Integral between 0 and 2, pi r squared minus r squared dx. Pi integral 0 to of x squared plus 2 squared minus little r, which is 2 squared dx. Okay, that's exactly what we were in our previous problem. But on the right, if you're not careful and you spin around the wrong axis, that's when we're screwed. 1, 2, we have a parabola going up. 3, 4, 5, 6. This is where the parabola intersects. Oops, let me try a different value. 2, 2, 2, 2, 2, 2, 2, 2. Okay. We said we're going to have a boundary right here. In this case, this is 2. In this problem, does it even matter? Take a look. If I spin around this axis here, do we end up with a washer or a disc? All right, I'm spinning around this axis here. You end up with a disc, right? So in this case, we don't even need the washer equation. We totally avoided our second equation. But you still have to make sure you got this disc equation right. In this case, it's the axis of rotation to the function. So it's 6 minus our x squared plus 2. So pi, 0 to 2, 6 minus x squared plus 2, do a parentheses there, square that dx. See, this became a disk problem. So we can't just say, oh, hey, we are given two functions, bam, that's a washer. It's always about our axis of rotation, and that can mess us up. Now, I could also change this problem a little more. I could have said instead, making this problem a little harder, I could have said taking this example here, let's run over here, and this is not a washer, but let's say we use the same idea. We have our y is equal to x squared plus 2, and y is equal to, this time, that's right, 3. Now this is going to cut into my graph. So we have our y is the x squared plus 2. Here's our y is the x squared plus 2, our parabola going up. We want to spin around, axis of rotation is y is equal to 6. Here's our number 6 up here. And we're going to see spinning up. And we're going to see spin around this axis here. But careful, if I say y is equal to 2, do you see how it actually cuts my graph off? So in this problem here, we have to be careful because I am not counting this anymore. So part of the problem stems here that we need to find out where they intersect. We'll call this C here, right? We'll call that C. So we're going to go start an integral problem. Now this is the part that's a little, you got to be careful because we're setting it up. Let's talk about this part of the graph first. Let me highlight this. Let's worry about this part of the graph first, and then we'll worry about the second part of the graph next. It's because we're still spinning this around. And when you spin around, it'll just be like a flat section. It'll be like a flat curve here. Be flat curve, and then it'll start to curve. Right? It's going to be flat. It looks like a Eskimo igloo or something, or a hut. So how do we do this? It goes back to us talking about what is the radius. What's the radius from here to here? Right, we're not going all the way down here anymore, right? We're not going all the way to the function. We're stopping. So the integral from 0 to c of pi r squared, which is radius of 6 minus 3. I want to make sure you guys are all cool with that radius here. The radius is here to here, right? Which is the value 3, not the function anymore. And then we're going to add this part here, which is 6 to the function, x squared plus 2. Integral from c to 2 of 6 minus x squared plus 2. Don't forget the parentheses because that's going to flip it. Okay, so I want you guys to be cool with the parts. And really, the way I'm setting up the integral, I'm not setting up till I actually see the picture to see, okay, this is one section and this is another. The way we find c also is when does x squared plus 2 is equal to 3, right? That's where they would intersect, and that's going to be some type of fraction number. Actually, you know what? Would this be a fraction? Oh no, I don't think so, right? X squared plus, oh yeah, wait. When is x squared plus 2 equal to 3? So yeah, x squared is equal to minus 2 is 1. X is equal to 1 plus or minus 1. We can only use a positive one. X equals to 1. So our c value is actually our 1. This would have been 1. This would have been 1. So we would have found that out anyways. Okay, so let's give you guys another problem. Let's do this one here. We'll say, here's my next example. The example is y is equal to 4, y is equal to 1 over x, and then axis of rotation. Oh no, sorry, we're going to be bounded by the graph. X equals to 2. That's our boundary. And we're going to rotate around the axis of, let's see, axis is x equals to 0. Sorry, not x equals to 0, y is equal to 0. There's a lot of information with these graphs. So let's just draw it out. You can draw a Desmos right now for you guys to figure out what it looks like. But by hand, this is 4. Okay. I've seen these graphs before. They are rational functions. So we have a vertical asymptote at 0, vertical asymptote at 0. And remember, these graphs look like these types of graphs right here. We're going to be stuck in the right-hand corner here, looking like that. So we are stuck at 4. We are stuck at 2. 1, 2, 2. And we're bounded by the graph. So this is my graph here. And we are going to rotate around the x-axis. Check it out. This is the x-axis over here, isn't it? So when we spin it around, the shape's going to look something like, Oops, let me draw my, try and mirror the box here. Mirror the box, mirror the box, mirror the box, and mirror the box. Okay, something like that. And we end up with a shape. You guys kind of see that? Kind of like a Play-Doh shape. Whoops. Yep. So let me switch colors here. So this is going to be, let me use black. So it's going to look like this. So it's a cylinder on the outside with a little shape like that cut out on the inside. Right? Kind of like a bun cake-ish. You see that shape? Okay, now it could be confusing, but here's the point. Don't let it confuse yourself. You can actually stop. Please stop at this drawing here. That's helpful enough. So we realized at first, is this a disc or washer because there's a hole cut out in the middle? This is a washer. If you want, you can automatically write this equation. Integral r squared minus r squared. R squared minus r squared. So we want to take our big radius. That will give us this shape here. This is my big radius, right? That's my cylinder shape. Good. And then we're going to cut out this small radius shape here. And this is actually finding two separate volumes. So let's go ahead and set this up. You could run to the answer. Let's run to the finish line. From 0 to 2, that's where we want to go, from 0 to 2, it looks like. Oh no, it's not a 0 to 2. Whoops. It's not 0, right? Because what happens is this point here is not 0. So when does 1 over x equal to 4? That's when x equals to 1 over 4. So we have to find out where they intersect, like we mentioned before. Because this doesn't ever actually hit 0. Remember there's a little gap here? There's a gap. And we're going to go all the way up to 2. Our big R was 4. Our little r, take a look here. Our little r is bounded by this equation here, which is the distance from this value to the axis of rotation, which is the equation 1 over x squared dx. So you can jump from here to here with a little bit of help finding where they intersect. So these can be a little bit tricky. Now, since this is multiple choice, they will give you hints. They will tell you that's not 0. No es 0, right? Not 0. But please don't take it for granted and say, oh, hey, look, it's 1 over 4. I'm not going to look it up. You have to look it up. And the way we look it up is we set the equations equal to each other to find out where they meet. I'm including most of these problems have graphs that I already laid out. Okay, so let's look at another question here. This is a weird one. And this is the equation y is equal to 2 square root of cosine of x. And y is equal to the square root of cosine of x. And we're going to bound ourselves from negative pi over 4. X is negative pi over 4 and x is equal to pi over 4. Okay, this is an example problem. So I don't know what this graph looks like. This is a square root of a cosine graph. Let's go ahead and graph this on Desmos. Now, let's see, we're going to go into 2 square root of cosine x and 2, well, just cosine x, oh, square root of cosine x. Okay, we're going to zoom in here. Let me actually give 2 more values. I'm going to say x equals to negative pi over 4. That's what they wanted. And x equals to pi over 4. All right, so we're bounded in this section. That's the region that we're in. Okay, in this case, we're going to rotate around. The axis of rotation is the x-axis. All right, so let's just mock it up over here. We have some type of parabola on top. Not really a parabola, but it's an arc, right? We have an arc on the bottom. And we're cutting it off. Negative pi over 4. Pi over 4. Now, the axis of rotation is over here at 0. So if I make a mirror image, we end up with a mirror image over here. Okay, I'm going to go ahead and try to draw the shapes. Whoops, darn, I linked up the wrong one. The inners and the outers. Ew, that was a little wonky. I need to delete this guy here. That one's too wonky. Okay, so you can see it looks like an olive. Right? Good job. We're going to find the area of an olive. Now this is what I need to stress right here. This graphic could be confusing. So please don't pay attention to this, all these lines I'm drawing. Right? I'm just trying to get your brain wrapped around it. You really only have to pay attention to this section right here. Just pay attention to this circle here. That's the only thing we're worried about. And the idea is we're taking a large circle and we're minusing the little circle inside. All right, that's how we're going to set this up. So we have to find out what the large radius is, and we'll find out what the little radius is. And that will set up our equation. In this case, we're bounded by negative pi over 4 and pi over 4. So negative pi over 4. Oops, let's go a separate integral. The volume is equal to the integral, don't forget the pi outside, of negative pi over 4 to pi over 4. And what is your big R? What is your little r? Dx. That's our jump to the answer. That's really what it is. Our big R is upper minus, in this case, 0, right? Which is our function. I think that's going to be our 2. Yep. 2 square root of cosine of x. Our inner function is going to be just, our inner is this, right, that's my inner radius, is just square root of cosine of x. And that's it, you're done. Now please don't write this. This is bad voodoo, okay? If you write 2 square root of cosine of x minus square root of cosine of x squared, if you write that as your volume equation, that is not it. When you write this, you're saying upper minus lower, whatever's left over, spin that.
Mr. Ko,
Yes.
for the integral, you put the negative one on top.
Oh yeah, whoops, I flipped it around. I'm sorry. You're right. I flipped it around.
Okay.
Thank you for catching that.
E.
Yep, you're right. I spun it around the wrong way. That would just give me a negative volume, probably. Okay. So this is bad. This is bad. Okay. And the reason why they're separately squared is because, remember, this is actually 2 separate integrals then combined. R squared, and then we combine them together to save time. That's the only difference. So please don't do that. This is bad. If you do this again, you're just subtracting your y minus your y. That leftover value, you're spinning around your x-axis. That's going to give you this shape here, which is not the shape we're describing. Okay. And that's it. That's washers. Okay. So how do you know if it's a disk or washer? A washer is a disk with a hole in it. And because there's a hole in it, we're going to subtract the 2 r values from each other, but do them separately. R squared minus r squared. If it is a disk, there is no hole in the middle. So we just look for what the radius would be. Okay.